Hi everybody, my name is Sayyid Shadi and I'm going to present our paper for Near Surface Geoscience 2020 conference. You see the title of our paper, which is the effectiveness of pseudo-gravity transformation in mineral exploration, an example from a placer magnetite deposit. I would like to start with an overview into the problem. The main objective of this research was to detect deep or concealed ore zones within a placer magnetite deposit into an active iron ore mine by means of ground magnetic surveying. So with the following situation, there are several probable challenges in here. The first challenge is that the presence of surfacial magnetite-rich zones can create high-frequency or high-amplitude magnetic anomalies that may interfere the signals from deeper sources, or it may increase the possibility or the intensity of the aliasing error in the final grid. Additionally, the irregular distribution of the magnetization in the subsurface makes every kind of 3D inversion difficult. Not only in terms of the modeling approach, but also in terms of the geophysical model validation. In fact, we do not know what is the exact shape of the ore. It could be in different parts, it could be in one single zone, so we are not sure about it. Here we have used a very simple, very well-known approach, that is the pseudo-gravity. We have used the pseudo-gravity transformation. It is well known, but it is not adequately discussed in the literature, either in the different applications or in the interpretation context. And in this case study, we show that it is highly effective under certain conditions. What is pseudo-gravity? The pseudo-gravity you are all familiar with. The potential flows are inversely proportional to the distance from the source, so consider the magnetic potential of an isolated pole or the gravitational potential of an isolated point source. They can be related to each other by the Poisson's equation. So under certain circumstances, the magnetic data would be transformed into a gravity-like response, and vice versa. The gravity would be transformed into a magnetic-like response. The second one is not interesting for us because interpretation of magnetic data is much more difficult with respect to gravity data, but this first option would be very useful. So gravity, the pseudo-gravity, is a gravity-like response that would be obtained if the body's magnetization would be replaced with the same density distribution, i.e. the magnetic susceptibility and the density follow the exact linear relationship. Additionally, it assumes that the magnetization is entirely induced, so no remnant magnetization present, but it could be a problematic assumption. But in some cases, if the remnant magnetization is not severe, the application of pseudo-gravity would be very, very interesting. So our case study, the Cook-Sombol deposit, you see the geological map in the upper right and the digital elevation model in the lower right. And as you can see, the magnetic surveying area is in the west of this mine pit, and it also includes the surrounding of the mine pit itself. The Cook-Sombol deposit, in fact, lies in the northeast of Iran in the Khaf district. which hosts one of the biggest iron ore deposits in Iran, the Sangan deposit, with approximately 1.2 billion tons of iron ore. So the design of the magnetic survey, we set the line spacing to 20 meters and the inline spacing to 4 to 5 meters. And it is also assigned that the magnetic base station measurements should be taken one reading per minute to be able to have the most accurate daily correction. In the figure below, you could see the TMI and the RTP grids. As you could see in the TMI map, most of the anomalies are just following the expected trends in the northern hemisphere, higher latitude, and I would like to note that the declination in this area is almost zero, so the locations of the positive and the negative poles are consistent with what is expected to see. And as you could see that there is a clear difference of the values of the magnetic field intensities in the southern part and in the central part of the map, and you would see the result of this variation in the RTP map that is highlighted the anomalies much more better. When we use the analytical signal in the mine pit, we have a high magnetite concentrations. You see that the mine pit has been clearly characterized by the analytical signal, and the upward RTP is showing that there might be an extended ore zone in the southern boundary of the mine pit. The first vertical derivative of the TMI is also like the analytical signal, but I would like to focus on the pseudo-gravity in here, that it is also similarly somehow to the upward RTP, but in fact it inherently highlights much more detail about the subsurface variation of the in fact magnetization or the presence of the magnetic minerals. If you just pay attention to the figures down below, you will see that there are some sections highlighted in here, AA prime and BB prime, and you would see that the AA prime section in here from the north to the south, and you could definitely see that there is an extension of ore zone and the ore zone continuity towards the south, which is highlighted by the magnetic data, especially the pseudo-gravity grid. And this is the BB prime section. It is also very greatly highlighted the extension of the ore zone towards the east of this study area, and the deep ore zone is being greatly characterized. So as the conclusion, we would like to say that the pseudo-gravity map highlighted the concealed magnetite-rich zones at depths that was not visible from the surfacial geological surveys, and we would emphasize that it highlighted the ore zone very accurately and with high precision. Consequently, if it is wisely applied, it can be a fundamental tool in the exploration of different mineral deposits. As to our limited experiences, we have seen its great application in the exploration of some porphyry systems and some other type of iron deposits as well. And I appreciate your time and your attention.